the first set of notes for Chapter 6, Thermochemistry. Not a bad chapter overall, it's not too terrible. So we start off here with a picture of some hydrogen combusting and some snow being made. These are both important thermochemistry concepts, and we'll talk more about the snow here at the end of this set of notes, so let's hop right into it. Energy, if you've had physical science or physics, is generally defined as the capacity to do work, the ability to do work. There's lots of different types of energy that are important to us in chemistry class and just as living, breathing beings too. Radiant energy is the energy that comes from the sun. This powers the earth, of course, starting with plants. You're familiar with that. Thermal energy is the one we're going to look at a lot in chemistry, in your labs, all that stuff. Thermal energy is the energy associated with random motion of atoms and molecules, so it's really very directly related to kinetic energy. Chemical energy, energy stored within bonds. We use that for digestion and that sorts of things. Nuclear energy, energy stored within neutrons and protons of the atom, and that's going to be responsible for things like powering our sun, nuclear energy plants, nuclear bombs, that kind of stuff. Doesn't take a lot of material really to make a pretty crazy amount of energy. And then potential energy is one you're familiar with. Hopefully is the energy available just due to an object's position. Flower pot sitting on a windowsill has the potential to fall, has energy because of its position. And to a certain extent, atoms and molecules, they have those as well. So we're looking at energy change here in chemical reactions. So heat is defined as the transfer of thermal energy between two bodies that are at different temperatures. They have to be at different temperatures in order to transfer heat, of course. Temperature is a measure of thermal energy. Temperature does not equal thermal energy, however. Temperature is more of a measure of the average kinetic energy of a substance, but it's not the total thermal energy of the substance and all the atoms in the substance. We couldn't really measure that. Temperature is just sort of our scale we use because it's convenient. So thermochemistry, which is what we're doing this chapter, is the heat change through chemical reactions. So we kind of define this as a system. The system is the specific part of the universe that we're interested in. Could be a calorimeter, for example. It could be the inside of a rubber tire. Anything is, there's the system, then there's the universe, which is anything outside of the system. So here we've got some sort of bottle without a lid. That's called an open system, which means there is an exchange between the system and the universe, everything surrounding that system. So in an open system, you can exchange mass, so we could pour more liquid in, pour liquid out, and we can exchange energy, which is our heat lost or gained to the system. We then have a closed system. Here we've put a stopper in this bottle. So in a closed system, we're not going to be able to exchange that mass anymore. We can't pour any more liquid in or pour any liquid out, but we can still exchange heat. If this were, for example, hot coffee or tea, it would eventually cool down through that glass. So we can still exchange energy through a closed system. And then here is a system that's kind of best to study. This is what you'd call an isolated system. So maybe if you've got the best coffee thermos ever, and it exists in like sort of a vacuum, then we're not going to get any mass in or out. So perhaps it's not the best coffee thermos ever because we'd like to take the lid off. And we're not going to get any energy in and out either. So, ideally whatever temperature this is at is pretty much going to stay at that temperature because it's an isolated system. So we're not exchanging anything in an isolated system. So exothermic and endothermic, hopefully terms you're a little familiar with. Exothermic is pretty easy because therm is heat. Exo is, to exit or to leave. So this is heat leaving. So it's a process that gives off heat. So if we're giving off heat, then we must be giving it from the system to the surroundings. So here we've got hydrogen and oxygen gases forming liquid water. And so just thinking about it from a kind of kinetic molecular theory, if we have a gas with lots of energy, liquid state with less energy, then they must give off energy to get to that state. And so here we have plus energy. So if it's giving off energy, that would be exothermic. Again, gas to liquid, giving off energy. Exothermic, that's just water, gaseous water forming liquid droplets. Pardon me. Endothermic process would be the exact opposite here. Heat is being supplied to the system, or you could say heat is being absorbed through the reaction. So we have energy on the reactant side, plus our mercury oxide. So we're kind of burning mercury oxide, and it's a solid, and it's going to become liquid mercury and gaseous oxygen. And here, energy plus solid water, so an ice cube, plus energy from its surroundings, endothermic, gives us, liquid water, ice cube melting. Not too terrible, I hope. So if you were to draw this as energy change here, this arrow going up, we could say gaseous hydrogen, gaseous oxygen yields liquid water. That's exothermic. We are giving off heat to get to that state. And then the opposite end of this would be here to get from our mercury oxide to our liquid mercury and our gaseous oxygen, heat has to come in to the reaction from the surroundings. So just the difference between exothermic and endothermic there. So thermodynamics then is the study of these changes between how much heat's changing and what type of heat, what kinds of energy are involved in the reaction. So state functions are any property that's determined by the state of the system, regardless of how that condition was achieved. Energy is a state function, and so here, two hikers started a trail. Their potential energy, one walked straight to the top of the mountain, has a much higher potential energy than he did when he began. The other hiker takes a different route, but still makes it to the same elevation, so he's at the same potential energy. And so the potential energy of hiker 1 and hiker 2, they're the same, even though they took different paths, because energy is a state function. All that matters is we got from point A to point B. It doesn't matter how you got there. If it's a one-step chemical reaction, great. If it's a three-step chemical reaction, great. Energy change is the same. That's what we're concerned with. So delta is something we're familiar with, change in. So that's final minus initial. Energy final minus energy initial was their change in energy. And we can do the same thing for state functions for pressure, volume, and temperature. And so then any of these, delta P, same thing, delta V, same thing, delta T, same thing. And those can be negative as well, so just beware that, if temperature is cooling and you say temperature final, 10 degrees minus temperature initial, 50. You can have negative deltas, that's fine. So it takes us to our first law of thermodynamics, one you're probably familiar with. Energy cannot be converted, or energy can be converted, from one form to another, but it cannot be created or destroyed. Sorry if you can hear that in the background. My dog is dreaming right now, and she's really making noise. So here we have the energy in our system plus the energy of our surroundings equals 0, because according to the first law of thermodynamics, energy has to either be in the system or it has to be in the universe. It can't be anywhere else. So all of the energy we have has to be surroundings or our system. Those are our only options. And so we can rearrange that if we want to. The energy of our system is equal to the negative energy from our surroundings, which kind of makes sense. If your system got energy, then it got that energy from its surroundings. So that's sort of how we get that. So here we have something burning. Looks like propane. Propane plus oxygen is going to yield carbon dioxide and water. When you combust things, it's normally a safe bet to say plus oxygen yields CO2 and water. Wow, she is really dreaming over there. Anyways, exothermic chemical reactions is what that would be, of course, and it's burning, so pretty safe bet to say exothermic. If something's burning, it's going to give off thermal energy, kind of a no kidding sort of point. So where this comes into the first law of thermodynamics is that all the energy we lost by combusting this gas has to be energy gained by the surroundings or the universe. Anything outside of that system is going to be warmer because of that burning methane. Propane. So to write that first law of thermodynamics, we could say that the change in energy is equal to Q plus W. Q being heat, W plus work. And sometimes those will have the same units. A lot of times it'll be joules, kilojoules, something like that. So delta E is the internal energy of a system. Q is the heat exchange between the system and the surroundings, and W is the work done on or by the system. Sometimes you do work on the system, sometimes the system does work on the environment, so it just kind of depends on what sort of situation we're looking at. So you can calculate work. If it were for a gas, it's negative P delta V, and that's a gas that's expanding against a constant pressure. You'll note that it's negative because if the gas is doing the work, then that pressure is negative. So if the work is done by our system, then the sign is negative. So you kind of think of work done on the systems being positive. If you had a bike pump and you plug the tube with your hand and compress that bike pump with the other hand, you'd be doing work on that system of gas in the bike pump. So you'd be getting positive work to the system. Then if you release that pressure, keep the tube plugged, but let go of the handle that you use to work the bike pump, then the gas could push that bike pump handle back out, and that would be the gas doing work on its surroundings. So it'd be negative work done by that gas. So you can do work on a gas, and the gas can do work on the environment. So we do have to be respectful of those signs. Here, heat's the same thing. If heat's absorbed by the system, that's endothermic. We have positive heat. We also have negative heat. If the system's releasing heat, then heat would be negative. So hopefully you find those pretty logical. So let's look at work. You can do work on a system. Work equals force times distance. That's kind of a physics thing or physical science thing. And here we said work is negative pressure delta V for a gas doing work on a system. And so here we see initial gas, this is atmospheric pressure perhaps. The gas is allowed to do work and to push up this piston sort of situation. And so we have a delta V. How much volume did that gas change? So here we're deriving some formulas for force and distance equaling work. We're relating these two equations to show you that they are the same. But you'll note that work is not equal to work final minus work initial. So it's not what we called a state function earlier. Pressure is, volume is, you can use all of those, but don't use work as a state function. And so here we get kind of the example of this, and we'll do problems like this in your book. So here's one you'd want to try on your own if you want. A sample of nitrogen gas expands in volume from 1.6 liters to 5.4 at constant temperature. What's the work done if the gas expands against a vacuum and against a constant pressure of 3.7 atmospheres? So why don't you pause the video, use those equations that we just learned, and see if you can't solve that. Okay, so hopefully you paused that and gave it a shot. If you did, you probably figured you should use this equation, and you'd be absolutely right. They give you atmospheric pressure of 3.7. That's what the gas is working against. And then our delta V, 1.6 to 5.4. So we know delta is final minus initial. It'd be 5.4 minus 1.6 liters. Give us something around the order of 3.8. Now, for A, it asks us to expand against a vacuum. So what's the pressure in a vacuum? Of course, the answer is 0. There's no pressure in a vacuum. And so anything multiplied by 0 would be 0. So if a gas expanded against a vacuum, it would be 0 joules because it's not doing any work against the vacuum. Now, if we did do it against the pressure for B, 3.7 atmospheres, then it would be our 3.7 atmospheres, our 3.8 liter change from before. And we would take work is equal to negative pressure multiplied by volume change, and we get a negative 14.1 liter atmospheres. Now you can get that to joules with this conversion. You might want to commit that to memory because we are going to use it a lot this chapter. 101.3 joules in 1 liter atmosphere. And so from here we had liter atmospheres from our volume and pressure. And now we can cross that off and get to joules at negative 1430 joules. So that's how much work the gas did. And you want to check your work. If we have negative work, then our gas should have been doing work on the system. And here it says the gas expands in volume, so we know it's doing work on the system, and that makes conceptual sense. So do feel free to check that. All right. So we're going to look at making snow now, and this is the slide we'll end on, so get you through the first few questions of your book. When you go to make snow, basically A lot of places where they have ski slopes, snowboarding slopes, whatever you want to call them, they don't necessarily get snow year round because the humidity might not be right, but they are at an altitude and temperature where they can sustain snow. It's financially feasible to make it. It's expensive, but if you make a lot of money on the slopes, then you can make it. And what they basically want to do is wait until their temperature and humidity are about right for making snow, and then they are going to use these laws we're talking about in thermodynamics, um, the energy change, the work they're going to do on a system, and the temperature they want that system to be at. And what they're going to do is take water and like air compressors, put a lot of pressure behind that water, and they kind of blast this pressurized, already cold water up high into the air. And when it's up there, it sort of freezes and falls as snow. So it works all right to make snow on some slopes. It is expensive, but it's just kind of an example of applied thermochemistry. So we will stop there for our first